Hello, and welcome to this tutorial on ultrasound and elastic media. We'll begin by defining what we mean by an elastic medium, and in this case, that's one where there is a linear relationship between stress and strain. Within this tutorial, we'll be discussing isotropic materials, which support longitudinal and shear waves. Loss and dispersion artifacts are associated with viscoelastic media, and these are covered in another tutorial. We'll begin by looking at the rheological model, which for an elastic material is a single spring, denoted by an elastic modulus m. We recall from our high school physics that for a one-dimensional spring, force is proportional to modulus times extension. However, if we need to look at Hooke's law in 3 dimensions, it's more appropriate to talk in terms of stress, strains, and the elastic constant matrix. Let's consider those elastic constants in a little more detail. For a completely general material, the elastic constant matrix would contain 36 terms. However, if we constrain ourselves to consider isotropic homogeneous elastic media, and make sure that we take appropriate account of all the necessary symmetries, this reduces down to simply 2 constants. They are the Lamé constants mu and lambda. And we can see how they populate the elastic constant matrix as shown. Notice here that the upper left quadrant has got diagonal elements of lambda plus 2 mu and off-diagonal elements of lambda. And the bottom right quadrant has got diagonal elements of mu, where all other terms in the matrix are 0. And now let's look at the relationship between wavespeed and modulus. As a general rule, wavespeeds can be calculated by taking the square root of a modulus divided by density. For any given specific wavespeed, we just need to select the appropriate modulus. Consider, for example, longitudinal wavespeed. In this case, the modulus of interest is the expression k plus 4/3 g, or equivalently, in terms of the Lamé constants, lambda plus 2 mu. This combined modulus is so important in ultrasonics and acoustics that it's sometimes referred to as the plate wave modulus. Note, this expression also holds if we are looking in fluids. Although in fluids, shear moduli tend to take the value of 0, and therefore in practice, the plate wave modulus reduces just down to k, the bulk modulus. If we're now interested in shear waves, then this is simply the modulus g, our shear modulus, alternatively in terms of Lamé constants mu. Note here that k plus 4/3 g is always larger than just g, which is why the longitudinal wavespeed is always greater than the shear wave speed. We'll now consider plane normal incidence excitation of waves in an elastic medium. A force is applied orthogonally to the material surface. This is our normal incidence. And because it's a plane force, all particles in that first column experience the same force, magnitude and phase. Initially, that force will cause the particles to displace to the right-hand side, before returning to their equilibrium position. In so doing, they exert a compression to the particles immediately adjacent to them. This second column of particles will also displace, again returning to their equilibrium position, but in so doing, exerting a compressive force to the third column. In this manner, the compressive force propagates through the material. Because the exciting force and the direction of propagation are parallel, we term this a longitudinal wave. If we're to consider anything other than plane wave normal incidence, we need a closer view of what's happening to the interparticle bonds within the material. We'll consider a particle of interest shown in pale blue, and we'll apply a force to that particle only. Let's see what happens as that force is applied. Our particle of interest moves to the right, which places the bonds above and beneath it under tension, whereas the bond to the right-hand side of it is now under compression. Let's see what happens as we allow these forces to propagate. This has resulted in the first nearest neighbours above and beneath being drawn towards our particle of interest, whereas the first nearest neighbour to the right-hand side has been pushed away. But that means that the second nearest neighbour bonds are now also in tension. Let's allow those to propagate. We can see now that we have got a wave that is propagating away from the particle of interest. In fact, because the starting force was at right angles to the direction of propagation of that wave, it's a classic transverse wave, which in acoustics we call a shear wave. Now let's look at the combination of those two wave modes. If we consider a general elastic material where a force is applied to two particles on the surface only, again coloured pale blue. As this force propagates, we see that there are shear waves travelling in the vertically up and vertically down directions, and a longitudinal wave travelling horizontally. In fact, even this is a simplification, because in the pale blue areas we will find that there are both shear and longitudinal wave modes propagating. Let us now consider what happens when a propagating wave encounters the interface between two elastic media. For simplicity's sake, we'll start off by considering fluid media only at normal incidence. And to do this, we need to consider a new quantity, Z, the acoustic impedance. Now, acoustic impedance is sufficiently involved subject that there's an entire video tutorial dedicated to this elsewhere in the Precision Acoustics series. But for the moment, for this tutorial, we'll consider the characteristic acoustic impedance as being the product of wave speed and density. Here we have a diagram of the two media of interest. We have a wave normally incident on the interface from medium 1, and there is a reflection at that interface. The amount of pressure wave which is reflected is given by the pressure reflection coefficient, which is the difference of the two impedances on either side of the interface over the sum of the two impedances. If we're concerned with intensity quantities, then there is also an intensity reflection coefficient, and this is simply the square of the pressure reflection coefficient. Some of the signal will be transmitted across the interface, and the amount of pressure that is transmitted across the interface is given by 2 times Z2 over Z2 plus Z1. As we saw with the reflection case, there is also an intensity transmission coefficient, but this takes a slightly different form. We'll increase the complexity a little on the previous case, and although we still have two fluid media in contact with one another, we notice that the incident wave is arriving at θ1 to the normal, to the interface. As previously, we'll see this wave reflect, and because both the incident and reflected wave are in the same medium, the angle of incidence and reflection is the same at θ1. The pressure reflection coefficient takes a similar form as we saw for the planar interface, but now we're specifically looking at the normal component. In fact, we can find the normal component of either Z1 or Z2 by considering the characteristic impedance divided by cosine of the relevant angle, again in this case θ1 or θ2. There'll also be a transmitted wave, and because we've got different media, and we know that we will have refraction going on, θ1 and θ2 are not necessarily the same. Once again, our pressure transmission coefficient takes a similar form, except that we're looking at the normal component again. And if we're looking to try and determine θ1 and θ2, we can use Snell's law. We'll now consider the interface between one fluid and one solid material. Here, the fluid is on the left-hand side and is medium 1, and the solid elastic material is medium 2. We have oblique incidence, as we've seen previously, and therefore our angle of incidence and our angle of refraction are the same. Given that we're in a fluid medium, these are only longitudinal waves. However, in the solid material, we will have both a longitudinal and a shear wave. We've seen previously that longitudinal and shear wave speeds are different, and therefore we find from Snell's law that those angles of refraction will be different. Importantly, in this case, we've had mode conversion. A longitudinal wave in has become both a longitudinal and a shear wave in the transmitted medium. Our final case to consider is a solid-solid boundary at oblique incidence. As previously, we have an incident longitudinal wave at angle θ1 to the normal. And as we saw in the previous slide, there are two transmitted waves in the solid medium corresponding to the shear and longitudinal waves. However, because the incident wave is also solid, we will find there are two reflected waves, again one shear, one longitudinal. Snell's law allows us to work out the angle of all of these, as long as we know the longitudinal and shear wave speeds in both medium 1 and medium 2. But critically now, we have mode conversion in both media. An incident longitudinal wave in has resulted in 4 wave modes out. 2 reflected, 2 transmitted, 2 shear, 2 longitudinal. So within this tutorial, we have seen that wave speeds in elastic media depend upon the elastic constants. We've also seen that an oblique incidence on an interface with an elastic medium will cause mode conversion. This can lead to fields becoming complicated very quickly with multiple wave modes propagating. We hope you found this video interesting. If you have, please come back and find some more of the Precision Acoustics tutorial series.